Hello, my darling. So we are going to continue looking at applications of the integrals, and we're going to look at total change and total accumulation, okay? Because the velocity of an object in motion is not the only rate that we can integrate to get something. We have seen that accumulation or net change problems present us with a scenario where we are often asked to calculate the value of some quantity accumulated over time, and that involves an integral. So here's an example. The number of liters in an oil tank is changing at a rate. So even though it doesn't look like it, R of t is a derivative because it's a rate of change. So R of t is 0.26 t liters per minute, that's our unit, where t is the time in minutes. Initially, the tank contained 14 liters of oil. So at time 0, there were 14 liters of oil. Write an expression that can be used to find the amount of oil in the tank after 10 minutes. So we start with the initial amount plus the integral from the starting time, which is 0, to the time we want, which is 10, of our rate R of t. And what was R of t? R of t, here it is 0.26 t, and don't forget to put your dt on there. So this right here would be the expression, and we could actually go ahead and find the value. So it would be 14 plus the antiderivative of 0.26 t. We add 1 to the exponent, divide by the new exponent, and we're going to evaluate from 0 to 10. So this is 14 plus 0.13, and the t squared, we're going to plug in the 10 first, minus plug in the 0 and square it. So that's going to give us 14 plus 0.13 times 100, which is going to give us 14 plus 13, or 17 liters of oil in the tank. Ta-da! Now, let's describe the meaning of each expression in context to the given scenario, okay? The function W of t gives the number of water bottles produced by a manufacturer by time t in hours on any given day. Explain the meaning of the expression, the integral from 4 to 8 of W prime of t dt. So W prime is like having the velocity when W is the position, okay? So it's the change in the production. So it's how many water bottles are produced. So it's the number of water bottles produced from time t equals 4 hours to time t equals 8 hours. Remember, you have to have a noun, unit, and time. All of that has to be there, okay? Next one, the amount of oil being drained from your pickup truck, that's not good, is decreasing at a rate, R of t, quarts per minute, where t is the time in minute. What does the expression below mean? So again, this is the integral from 3 to 4 of a rate or a derivative R of t dt. So that's a change in what there was. So when did this happen? From time t equals 3 minutes to t equals 4 minutes. What happened? 0.5, but it's negative. So if it's negative, it means it came out. So 0.5, so half a quart of oil drained from the pickup truck. That's not good. You lost half a quart of oil in a minute. Not good. That truck needs service. All right, so Kevin got a gift of $500 from his grandparents for graduation. He deposited the gift into his college savings account. Kevin's saving grows at a rate of R of T hundreds of dollars each month, where T is the month and year. So remember, this is how much he gets. This is the change in the money. This is the start. Now wait a minute, he started with 500. Why does that just say 5? Because it's 500s of dollars, and that's why we don't have to write 500. Okay, so what does this mean? So time 1 is the first month and 12 is 12 months later. So by the end of 12 months, or after 12 months, whichever way you prefer, Kevin's account had a total of, now remember, this 24, but our unit is $100. So you could write $2,400 or make it $2,400 in the account. Okay, good. Okay, so now we're going to look at some of these total change problems, and of course we're going to look at them numerically, graphically, and analytically. So here's a numerical problem first. A city bus is accelerating from 0 to 18 seconds. The data for the acceleration A of t is recorded in the table below. If the velocity at t equals 0 is 6 feet per second, that means v of 0 equals 6 feet per second. Find the approximate velocity at t equals 18 using a trapezoidal sum. Okay, so if I want to find the velocity at 18, we would need to know our starting velocity, which is 6, plus the integral from the starting time is 0 up to, we're going to time 18, and we integrate our acceleration dt. We don't have an acceleration function, so we have to use the trapezoidal sum. So it's going to be 6 plus. Now before I do a trapezoid, look at your t's. That's changing 3, 3, 3, 3, 3, 3. Awesome. Delta t is 3 for each change. Awesome, awesome, awesome. So that means we can use the rule 1/2 times our delta t is 3 times, now we can use our first function height, which is 1. Do not write f of 0. If you're going to write it in function notation, it has to be a of 0. Plus 2 times all of these acceleration values except for the last one. 4 plus 6 plus 8 plus 7 plus 9 plus the last value. Because remember, in a trapezoid, all the sides except the first and the last are used twice. So now we have 6 plus 3 halves times 1 plus 10 is 11, plus 2 times, let's see, that's 10, that's 15, so 25 plus 9, that's 34. So we have 6 plus 3 halves times 10 plus 68. So now we're looking at 6 plus 3 halves times 79. 6 plus 3 is 79 divided by 2 is 39.5. So 6 plus, if I multiply by 3, 118.5, and then we add 6, that's 124.5 units are feet per second. Don't forget those units on your answer. All right. Now, let's look at a graphical problem. So the graph at the right shows the rate in gallons per hour at which stormwater is being pumped from an overflowing canal. Find the appropriate number of gallons pumped from the canal in the 24-hour period. So if we want to know the total that was pumped from the canal, that's the integral from 0 to 24 of the rate R of t dt. Now we are supposed to approximate this. The best approximation we know is a trapezoid, right, when we have a graph. So we're going to use a trapezoidal approximation. Now in order to do that, let's see if we got these heights. This height is at 100. That's not bad. This height is at 125. This height, when we're at 8, That's 8,135. This one here, let's say this is 12,130. 16, let's say that's 110. 20, that should be about 85. And at 24, that's about 65. Okay, so now we're ready for our trapezoidal rule. Our trapezoidal rule is 1/2 times, what's our delta t's? We went from 0 to 4, 4 to 8, 8 to 12, 12 to 16, 16 to 20, 20 to 24. The delta t on each of them is 4. Awesome, we can do this in one step. So our delta t times our function value at time 0 is 100, plus 2 times our function value at 4 is 125, plus 135, plus 130, plus 110. We're taking all these heights, plus 85, but then I'm going to close it before the last height, because the last height does not get doubled, just like the first one. So now half of 4 is 2 times 165 plus 2 times 125, 135, 130, 110. That's going to be 585, which is 2 times 165 plus 1170, which is 2 times 1335, or 2,670 gallons. Okay, 2,670 gallons of stormwater were pumped out. Awesome. All right, guys, there we go. Several total accumulation problems using integrals, both numerically, graphically, and analytically. Have a great day. Bye.